Okay, so let's get started. Welcome back to MAT1841. Today, we are going to be talking about VC dimension, and we're going to be talking about statistical classification. So I promised earlier in this class that I wouldn't talk about most classical machine learning. Today and tomorrow are going to be the closest we're going to get to talking about sort of more popular machine learning methods. We're still not going to be really talking about it, but we're going to be talking about some of the theories surrounding generalization. What just happened? I want that in blue. So we're going to start by talking about statistical classification and set systems. So this is in chapter 5 of your book, I think. It's online. I forget exactly where it is, but so we're going to go ahead and get started with a couple of definitions. We're going to start by defining a set system. A set system, X and H, consists of a set X and a class H of subsets of X. Okay, and so like you might be starting to make connections between lists and other concepts you've seen in mathematics, but for our purposes, we're actually going to keep it pretty grounded in more applied things for now. So for example, X could be the set of all possible emails. And H could be, it's a collection of subsets. So H0, H1, etc. Where, for example, H0 is a subset of X equals set of all spam emails. And maybe H1 in X is the set of all seminar emails, which you may or may not consider spam. Hopefully you don't. But there might be some overlap between these concepts, depending on how you want to do your classifications. So now, once we've done that, we have a set system. We can define what this set system is able to tell you. So, and we're going to do this by defining a set system, by saying that the set system X, H shatters a set A contained in X, if each subset of A can be expressed as A intersect H for some H in our concepts in our class. Okay, so basically what we're doing is we're trying to formalize the sense of we have a set system, a set of things X, and we have some set of some class of concepts. And we're asking how much can we separate a set based on the set of concepts? So can you distinguish all of the items in the set and all the subsets of items in the set by some combination of the concepts in H? And once we have that, we're going to define the VC dimension, which I am not going to be able to pronounce, the Vapnik-Chervonenkis dimension. I will be calling it VC dimension henceforth because I don't want to butcher that name more than I already have. So the VC dimension of H is the size of the largest set that is shattered, of the largest set shattered by H, where X is implicit here, of course. So since we're talking about set systems. Let's give a couple of examples. So let's start with the example of we're going to let X be the real plane, and we're going to let H be the set of axis parallel rectangles. Okay, so you can completely characterize so H is an infinite set of subsets where you can characterize it by the bottom left and the upper right of all these rectangles that you have in the plane. So, well, let's start with the easiest one. Can you shatter a single point? And the answer to this is yes. This is trivial to shatter. You can put a box around the point, and so then the point's in your rectangle. You can put a box outside that doesn't include your point, and so the empty set's also in your is also expressible as an intersection with H. And so this is trivial to shatter. Trivial to shatter. 2 points. Can we do that? Well, this is almost trivial to shatter. So, well, you can have one box like this, and maybe another box like that to include both of them. And so for any 1 point, you can select all the 1 point subsets. You can select all 2 point subsets, and you can clearly select all the 0 point subsets. Well, this is almost trivial to shatter. Well, let's take a look at 3 points. So let's say I draw out 3 points. Let's say here. Oh, sorry, I'm drawing points in blue. Say here, here, and here. Well, in this particular case, for this particular orientation of my 3 points, this is shatterable. So I can have 1 layer, I can have 1 layer, and of course, I can also just get all of it. So again, we can shatter. Sorry, let me use the same colors. So again, can shatter 3 points. Okay, what about this collection of 4 points here? Can we shatter this set using our axis parallel rectangles? Why not?
If you take the subset of the left point and the top rightmost point, then any rectangle has to have a middle point.
Yeah, so but basically the issue is this orientation. So however we try to select things, you're not going to be able to get, the middle point is the problem because it's in the convex, all of the other points, and so it messes stuff up. So like, or you could try that also doesn't work. And so we can't actually shatter this set. Cannot shatter this set. And one way of seeing this is you can't get just the 3 outer points. So if you get the 3 outer points, then you have to get the inner point. Because cannot get just the 3 outer points. So this is not shatterable. So does that mean that the VC dimension of this thing is equal to 3? Well, let me ask for a poll of hands. Who thinks that the VC dimension of the set system is 3? Who thinks it's 2? Clearly it's not 2, right? Because we can shatter a set of the size 3. Who thinks it's 4? So can we shatter a set of size 4? So this is where you have to be a little bit careful because we've defined the VC dimension as the size of the largest set that's shatterable. And I have exhibited an example of a set of 4 points that is not shatterable. But there may be some other set of 4 points that is shatterable. And it turns out that all you have to do is make sure there is no middle point in this particular case. So if I set up my 4 points like this, then this actually does turn out to be shatterable because you can get like list box, list box, list box, and so on. And of course, the entire thing. And by symmetry, you can see that you can get all of the subsets. So, but there does exist. I'm using the wrong color. That's all right. There does exist a subset, or sorry, a set we can shatter. So the VC dimension of this thing is greater than or equal to 4. Okay, well, let's take a look. What about 5 point sets? So that's the question. Let me put that in purple. Can we shatter all 5 point sets? So things are clearly getting harder now because you have to worry about points being inside of the sort of convex hull of other points. And it turns out that for 5 points, you end up with this problem where for any set of 5 points, you can consider a rectangle, containing all points, and we're going to shrink it to get sets of size 4. But now when you do this, if you clearly you can take some big enough rectangle and you can shrink it and you can get every possible like rectangle, right? So this process has to be able to get, if this process allows you, if the set is shatterable, then this process should allow you to get any of the sets of size 4. But notice that you can only remove points that are extreme in some way as the first point removed, right? So as you go down, the first point you remove has to be the top point. As you go from the left, the first point you remove has to be the leftmost point. But now there are only 4 directions you can come from because we're axis aligned rectangles. And so that means as you're going in, if you start with, say, this box here, if you go in from this direction, then you can get rid of this point, but you can't get rid of any other point. And so there are only 4 directions, which means you can only get rid of, there are only 4 points that you can uniquely get rid of to make a 4-point set as you go in. So there's some point that you can't uniquely get rid of using this method. And so therefore, you don't have the 4-point set with that's omitting that remaining point. Now you might ask, well, what if there are 2 points at the same time that are at the same level of extremeness? So the 2 points that are both topmost. Well, in that case, as you go past it, well, you only have a 3-point set, and so you still don't have a 4-point set. And so therefore, this is actually not shatterable. So this implies that the VC dimension of axis parallel rectangles is equal to 4. And somehow this VC dimension is allowing you to capture the sort of expressive capacity of our class of models, which are these axis parallel rectangles. So we'll go into that a little bit more in more detail, but this is, if you know any machine learning, this is sort of what we're getting at right now, which is how much capacity does this particular set of models have based on our parameterization? And it turns out that, well, any 4-point set, you can get any one of the subsets of a 4-point set, but not of a 5-point set. And somehow it's sometimes good that you have a low VC dimension, because if you don't have enough ability to get all subsets, then that means it's harder for your model to memorize stuff. And so you may have heard of things like generalization error, where your model learns to memorize the training data. If your model is sufficiently simple enough, and then it doesn't have enough complexity and not enough degrees of freedom, then somehow you might be able to prove that you can't memorize stuff. And that's one of the uses that we'll see tomorrow about VC dimension. But today we're first going to talk a little bit more about VC dimension and prove some facts about the VC dimension. So that was one example. Let's give a couple more examples. What color are they using? Red. So let's give another example. Let's say x is equal to the real line. And let's say h is equal to closed intervals on the real line. Well, what's the VC dimension of this? So the VC dimension of this is actually only 2. Because if you have 3 points, you can't ever get the 2 side points, but not the middle one. So it's the same sort of argument, but just a little bit easier for a list because you don't have to worry about the different directions. Let's see. What if x is, we're going to stay on the real line, but instead let's have our class of concepts as pairs of intervals. Any guesses as to the VC dimension of this thing? Yeah, so this ends up being 4. And you can just logic your way through all the different possibilities for 4 points, and we'll see that you can see all the different sets. And once you get to 5 points, then you run into the same problem that you had with the previous example. Let's give another one. So let's say, what if x is equal to the real line and h is equal to the set of all subsets of R such that A is finite. So all finite subsets of R. So what's the VC dimension of this? Well, you can get anything finite. So like, so this is infinity, yeah. Because for any finite set, you can clearly, well, pick things out. We're not going to deal so much with infinite sets just because it makes life complicated. But for our purposes, the VC dimension of this is infinity. How big an infinity, we're not going to worry about. And let's give a couple more, just so that we get the flavor of these things before I move on to proving facts about them. Let's say that x is equal to r squared, and h is the set of convex polygons. Okay, so now we're starting to get into things that are a little bit more realistic, because you may actually want to be working in R to the n or whatever and deal with like convex polytopes as your set of as your class of concepts. So separators, basically. If you're thinking about this from a machine learning perspective, think about these like the hyperplane separators that you'd see with like an SVM type model. So if I have convex polygons, how many different, how big of a set can I break up into all of its subsets? I'll give you a hint. I'm going to arrange all my points in a big circle. So it turns out that with a convex polytope, you can't actually get any subset of the points once you arrange them in a circle. And it takes a little bit of convincing, but the VC dimension of this is actually infinity. And yeah, because you can like do things like lat or whatever. Okay, let's see. So we're starting to get closer to the range of things people might actually do. Let's give one now that people really do use all the time. So let's let H be the set of vectors X such that W transpose X transpose is greater than or equal to T for some vector W. So this is the set of affine half spaces. Okay, so you can think of this as a hyperplane. So you can really actually think of this as a hyperplane separated now. So basically, you have some hyperplane in your d-dimensional space, and you're separated into two halves, and you're taking one of the two halves. And by taking a negative sign, you can also take the other of the two halves. So you can get any half space now. Well, I don't expect you to know this one off the top of your head, because we're going to spend some time actually proving this one. But what we'll find is that the VC dimension of affine half spaces is actually equal to d plus 1, where d is the dimension of your space. And let's prove this. So proving this will take a little bit of work, but we'll do it in two parts. The first is we'll show that it's at least d plus 1 by exhibiting, like proving that it's at least something, all you have to do is exhibit some set that it shatters. So that's in some ways the more easier direction. Whereas proving that it's no bigger than that, well, then you have to show that for every set of size d plus 2, it can't be shattered. So this lemma is going to be VC of H is greater than or equal to d plus 1, where, of course, H is the set that we just defined. So affine half spaces. Yeah, on the plus sign of the transpose. X is greater than or equal to T. And well, the proof of this is we just need to exhibit a single set. So let me define one for you. Let's let S be the set. We're going to start at 0. And then we're going to take all the elementary like directions, E1, E2 through ED, where each EI is the 0 vector, except obviously a 1 at position I. Okay. And so basically, you can think of this as if you're starting at the origin, you're going in every one of the primary directions and then building that polytope. Okay, so now we have lat, and well, now let's consider a subset of S. So let's let A contained in S be a subset. Without loss of generality, we're going to assume that 0 is in A, because if it's not, then take the opposite one, basically. So we're going to assume that 0 is in A, or you can just do a translation. It doesn't really matter. And we're going to let W now be the all ones vector minus the sum from A and A of A. What is this? So basically, we're letting W have 1 everywhere that you don't have the corresponding element from S. So this ends up being a vector of zeros and ones, 0, 0. And that means that this is in A. So 1 is in A, but 3 is not. So that's our W vector. And once we do that, well, then we just need to compute this out. And we know that A contained in the set transpose X transpose is less than or equal to 0. Why is that? Well, because we know that for all these things, when you take the dot product, you're not going to ever have a non-zero term in the same place, and so it's just going to be equal to 0. And so it's clearly contained in this affine half space that's less than or equal to 0. And we know that S minus A is contained in X such that W transpose X is greater than 0. And note that I'm being a little bit sloppy with the greater than or equal to or greater than, but you can just think about moving the hyperplane like an epsilon over, and you get the same thing. And then it fixes itself, basically. But this is true for any subset A, and therefore H shatters a D+1 point set, which implies that the VC dimension of H is at least D+1. Okay, so now proving the other direction is going to be a little bit harder. So to do that, we're going to have to first prove a theorem. This is theorem 5.9 by Radon. And this is a fact about convex holes. So if you have any set S contained in R to the D with the size of S at least D+2, this can be partitioned. Be partitioned into two disjoint subsets. Disjoint subsets A and B, such that the convex hole of A intersects the convex hole of B. Okay, so with this many points, then you have to have some intersection in their convex holes. There is a way of partitioning it such that there's an intersection of their convex holes. And you can sort of see how this would mess stuff up for our affine half spaces, but let's finish proving this theorem, and then we'll show how we apply this to prove the VC dimension of these affine half spaces. So, well, proof. Well, without loss of generality, we're going to assume that S is equal to D+2. So clearly, if it's true for a D+2 size set, then it's true for something bigger. So we're going to assume it's equal to D+2 with, and we're going to label all the points in it, A1 through a D+2. And now we're going to define a new matrix. We're going to define this matrix as with each of the columns being one of the points in our set S. So A1, A2, all the way through a D+2. So this is going to be a D by D+2 matrix. And let's augment this matrix. So let's augment this matrix with a row of ones underneath. So let's let B be equal to this matrix that has A on top and a row of ones underneath. Okay. And clearly the rank of this matrix, what's the easy upper bound on the rank of this matrix? What's the easiest upper bound on the rank of this matrix? Yeah, it's just D+1. This is a D+1 by D+2 matrix. So clearly the rank can't be bigger than the number of rows it has. But this means that the columns are linearly dependent, right? Because we have D+2 columns, and so clearly there's a linear dependency between them. Let's label all the columns B1 through BD+2. And note that each of these B's are just the A's with a 1 dependent on the end. And this is, a B is of course a D+1 by D+2 matrix. Okay, let's define a new vector, X, which is X1, X2 through XD+2 transpose, such that Bx is equal to 0. And we know this because we have this linear dependency, and because the rank is, well, I mean, it's a D+1 by D+2 matrix. So clearly there is some vector for which this is true. Without loss of generality, we're going to order it and say that X1 through XS are greater than or equal to 0, and XS+1 through XD+2 are less than 0. Okay, so just rearranging ordering the same way we did for one of our earlier proofs. Which proof was that? I feel like we did this for some proof earlier that I'm forgetting right now. But anyway, like we're just doing a reordering of all these weights. And then what we can do is then we can normalize. We're going to normalize it such that the one norm of the entire thing is equal, sorry, not of the entire thing, but of just the positive portion is equal to 1. Okay, so note that this is only normalizing it so that all the positive components add up to 1. Well, then we clearly know that the sum from I equal 1 to S of xi bi is equal to the sum from I equal S plus 1 to D plus 2 xi bi. Why is this? What have I done here? So you're basically just saying, if you expand out bx, you end up getting these two sides. And that's basically it. And you move all the negatives onto one side until they become positive again. But if this is true, well, this implies that the sum from I equal 1 to S of xi ai is equal to the sum from I equal S plus 1 to D plus 2 of xi ai. And we know that the sum over I equal 1 to S of our xi's is equal to the sum over I equal S plus 1 D plus 2 of our xi's is equal to 1 by our normalization, unless plus both sides are convex combinations, convex combinations of disjoint columns of A. But if both sides are disjoint, but if both sides are equal, our convex combinations and disjoint combinations, this implies the intersection. I can't speak. So this implies that the convex holes intersect. Convex holes of the two sets of corresponding points intersect. Okay. But what happens if they intersect? Well, if they intersect, well, then you clearly can't put a linear separator in between them, right? So, but then impossible to have linear separator of these two sets. And therefore, so a half plane cannot shatter a half space, cannot shatter a D plus 2 point set for any D plus 2 point set because of this theorem of radon. And this implies that the VC dimension of H is less than D plus 2. And of course, combined with our earlier fact example, this implies that the VC dimension of H is equal to D plus 1. Okay, let's see, how am I doing on time? Okay, I'm doing all right. Let's give one final example, which will be related. Let's suppose that we have a X is going to be R to the D again. And instead of using affine half spaces, we're going to let H be hyperspheres. Okay, so we're working with high dimensional hyperspheres now. So now there's some relationship between hyperspheres and hyperplanes, right? So does anyone have any, given that hint, does anyone, so we can show that the VC dimension of H is less than D plus 2. Why is that? And the reason for this is because if we can put spheres around two disjoint sets, well, if you have a sphere that's containing this set and a sphere that's containing this set, and the spheres don't overlap, well, that means that there has to be some hyperplane between the two spheres. So if you can draw, like, that's just one of the properties of the spheres and convexity. So when those sets are also divided by a hyperplane. A hyperplane. And well, we know the VC dimension of half spaces is d+1. So clearly the VC dimension of spheres can't be higher. And let's see, I'm also going to claim that the VC dimension of this is greater than or equal to d+1. Does anyone see how to do this? So the answer to this is actually the same construction as for half spaces, because there's this close relationship. And so this is by the same construction. By the same construction as half spaces. So it takes a little bit more work to see. So we'll actually exhibit this as well. So if we let S be equal to 0, E1 through ED again, then given a subset A contained in S, we're going to choose the ball center at A0 is going to be equal to the sum over A in A of each of our A's. Okay, so we're going to move the center up to be near all in the direction of all the points that are in our set. So remember, all the points in our set in this particular set are in some canonical direction. They all increase away from the origin on some axis. And so now we're going to take all of those and put our center up there. And if we put our center up there, well, then clearly that means that it's going to be closest to all the points in our set. And so if you take that point as your center and expand out that ball, once you get to distance 1, you're going to include all the points in the set, except maybe the point 0. And then you're just going to keep on expanding, and then you'll hit the point 0 before you hit any of the other points along the other axes. And so let's formalize that a little bit. Well, then we know that A0 minus A, oh, sorry, just A, not A1, is equal to, well, the root of A minus 1 for all A in A and A not equal to 0. Or sorry, not distance 1, but the correctest, like it will be closer to those points because it's along one of the axes that has the same value. And we know that A minus A is equal to the root of A plus 1 for all A not in A and A not equal to 0. And of course, it's the norm of A naught is going to be equal to the root of the size of our set. So clearly you can choose a radius that includes everything in your set and then optionally includes 0. So we can choose a radius such that this ball contains exactly A. Any questions so far? So I've just been giving a lot of examples of how you'd actually compute the VC dimension of these things. It turns out that for some of our analyses, we actually need something a little bit finer grained than VC dimension. So VC dimension only tells you the size of the biggest shatterable set, right? Another thing you might ask is, well, how many pieces can I shatter bigger sets into? So maybe a set of size 5 is the biggest set where I can shatter it into all 32 possible subsets. But maybe a set of size 6, I can shatter into 30 subsets, and that's still pretty good. And so let's define that formally by encoding that information into a shatter function, which clearly includes the information of VC dimension. So we're going to define for any set system, X and H, the shatter function. We're going to call this pi sub h of n is going to be equal to the max over sets of size n of the number of pieces you can shatter it into. So the maximum number of subsets of any set A of size n that can be expressed as A intersect H for an H in RH. And well, clearly we know that pi H of n is equal to 2 to the n for n less than or equal to the VC dimension of H, right? Because by definition, you can completely shatter any of those sets, and you have 2 to the n different possible subsets of a set of size n. Yeah, so there exists some set of that size that is completely shatterable, is what we're saying. Not necessarily every set of that size, of course. Okay, and I think I will, do I have time for, yeah, I have enough time to prove this. It's a little bit of a long proof. Hopefully we have time to prove it. If we don't, we'll come back to it a little bit later. So let's add a little bit of notation first. So I'm going to say n choose less than or equal to d is going to be, by definition, n choose 0 plus n choose 1 plus ... plus n all the way through n choose d. So just defining this, it's just n choose a subset of size less than or equal to d. And of course, this is less than or equal to n to the d plus 1. Because with n choose less than or equal to d, you're choosing it without duplication. And so n to the d plus 1 is going to get you n choosing n items d times with duplication. The d plus 1 is needed because you might have d is equal to 0. But I mean, it's pretty obvious that n, this is also less than or equal to n to the d if d is greater than 1. So, and this allows us to prove a very important lemma, which we're going to be using in tomorrow's lecture. So this is lemma 5.10 in your textbook of Sauer. So for any set system, xh of VC dimension less than or equal to d, then pi h of n is less than or equal to n choose less than or equal to d for all n. Okay, so this tells us the shatter function. This gives us a bound on the shatter function as a function of VC dimension. So even though the shatter function encodes all the information of VC dimension, it turns out that once you have the VC dimension, it also tells you something about the overall values of the shatter function everywhere. Not exactly, but it gives you a bound at least. And let's see, let's go ahead and give a proof. Actually, before I give the proof, let me add a little note here. So note that for n greater than or equal to 1 and d greater than or equal to 1, we know that n choose less than or equal to d is equal to n minus 1 choose less than or equal to d minus 1 plus n minus 1 is less than or equal to d. Why is this? Because you can consider canonically ordering your set of n elements, and then you ask, am I choosing the first element or not? So you have all different ways of choosing the first. So you have, and so this here is if we choose the first element, if choose first element, and this here is if not choose first. Because if once you've chosen the first element, then you have n minus 1 choose less than or equal to d minus 1. If you don't choose the first element, then you have n minus 1 because you know you don't choose the first element, and then you choose the remaining d. Okay, so this will become useful at the very end of this proof, but I thought it made more sense to put it here. So now, how do we prove this complicated thing? Well, as with many complicated combinatorial theorems, and this is basically a complicated combinatorial theorem, what's our favorite tool? Recursion. So we're going to prove this inductively. So but it's going to be a sort of complicated induction. So because we have two different variables here, right? We have both n and d. So we will prove by induction on both n and d. Now for induction, of course, we need a base case, and then we need some case that depends on it. And so we're going to actually give two different base cases. So I'm going to start with the base case of d is equal to 0. Okay, so this is a super simple base case. But basically, if the VC dimension is 0, well, that means that the only set you can complete the shatter is the empty set. And that makes life really easy. But let's actually write this out formally. So suppose that we have H1 not equal to H2 in our set. Then we know that there exists some A in X such that A is in H1 and A is not in H2, right? But then we run into the issue when H shatters the set A. That's a problem, which implies that D is greater than or equal to 1, which implies that H is actually just equal to a single item. So clearly we only have one item in the subset. And note that any set A contained in X has 2 to the A is equal to 2 to the A, to the size of A, subsets. So only set of size 0 can be shattered if we know that H is equal to 1, i.e. only the empty set. Which of course implies that pi H of n is equal to 1. And 1 is equal to n less than or choosing less than or equal to 0 elements. Okay, so that was an easy base case. The other base case is going to be, we're going to show that this is also always true if n is less than or equal to d. Why is this? Can any of you see list proof? So D is the VC dimension, right? So if n is less than the VC dimension, what does that say about how much you can shatter your set? Exactly. And when we write this out, so by definition, there exists a set of A of size n that can be shattered. So we know that pi H of n is equal to 2 to the n. And we also know that n choose less than or equal to d is equal to n choose 0 plus n choose 1 plus dot 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 plus through n choose n plus n choose n plus 1 plus dot 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 plus n choose d. What is n choose n plus 1? Yeah, there's no way of choosing n plus 1 distinct elements from a set of size n. And what's this over here? That's just 2 to the n. So this entire thing is equal to 2 to the n, and clearly this base case is also satisfied. So what have we done now? So we've proven like a series of cases. We've proven the case when d is less than d is equal to 0, and we've proven the case when n is less than or equal to d. And so now we're going to build an induction off of that. So the general ND is going to be a little bit more complicated. But the induction hypothesis that we're going to use is we're going to assume that our statement is true for n minus 1, d minus 1, and that it's true for n minus 1, d. Okay, so this is going to be a two-dimensional inductive argument. So if you write out all these different values, so let's say you had 0, 1, 2, 3, 4, so on for d, and let's give myself a little bit more space there. And we had 0, 1, 2, 3, 4, and so on for n. Well, what are our different inductive cases? Well, we have the base case here for d is equal to 0. So that means that this case is completely satisfied, right? So we know it's true for lots of parameters. And we know it's also true in this base case where n is less than or equal to d. So that means it's true for here. It's clearly true along the diagonal. And it's true underneath the diagonal. Right? And now our induction is basically saying that if we go from if that's true, then we can get this thing to be true. Okay, and so we're going to fill it in. So we proved the easy cases with the blue check marks and the green check marks. That was a super easy proof. And now we're going to use induction, this two-dimensional induction, to prove that's true for all the remaining possible values for n and d. And how am I doing on time? 5 minutes. I'm going to go a bit fast. Sorry about that. Okay, so now we're going to prove this inductive case. And the way we're going to start is we're going to select a from x with the size of a is equal to n, such that pi h of n subsets of a can be expressed as a intersect h for h in h. So this is a maximally shatterable set. So it's not a shatterable set because we're above that regime, but it's a set that exhibits the property that you can break it into as many pieces as any set of that size. And without loss of generality, we're going to assume that x is equal to a and replace h in h by h intersect a, removing duplicate sets. All right, so all we're doing is we're basically restricting ourselves to the list problem because this captures all of the salient features. Okay, so once we've done that, then we know that the size of h is equal to pi h of n, and each h in h is a subset of a. Okay. So we have this modified set system. So you can think of this as, i.e. we have some modified set system, which is a h intersect a for h in h. Okay, so modified set system. I think I needed another parentheses. Modified set system. And now we're going to create a couple more set systems. So we're going to create a new set system. Set system S1 by removing u from everything. That is to say, S1 is equal to the set here is a minus u, and H1 is going to be equal to h minus u for h and h. Okay. Well, then we know that for h contained in a minus u, if exactly one of h and h union u is an h, then h contributes one set to both h and h1. However, if both sets are in h, then h counts for two sets in h, but only one set in h1. Okay, so we're just doing a counting argument here. Plus, we know that the size of h minus the size of h1 is equal to the set of pairs h1 and h2, such that h1 minus h2 is equal to u. So the sets that differ by only u for h1 and h2 in h. So pairs of sets that differ only by u. And let's define a new set S2, a new set system, which is also a minus u as its set, but where we have h2 and h2 is equal to the set h such that u is in h is in h, and h union u is in h. Okay, so what we're doing here is this new set has all the h2, has all the h's that are the difference between h and h1. So plus we know that size of h is equal to the size of h1 plus the size of h2. And this implies that pi h of n is equal to pi h1 of n minus 1 plus pi h2 of n minus 1. Because h1 and h2 both correspond to sets a minus u. And so those are sets of And so these H1s and H2s are size one less on these sets. So each set in H1 by construction corresponds to a unique A minus U intersect H. And now, well, we're almost done, and I'm almost out of time, by which I mean I'm out of time. Sorry about that. The VC dimension of H1 is less than or equal to D, because otherwise H1 would shatter a set. I should write that down, because otherwise H1 would shatter a set of cardinality D plus 1. D plus 1, and then if H1 does, then so would H, right? And so clearly you can't have that be the case because you know our VC dimension of H is only D. And we also know that the VC dimension of H2 is less than or equal to D minus 1. Because if H2 shattered some set B contained in A minus U with the size of B being greater than or equal to D, then B union U would be shattered by H. So now what we have is we have an inductive hypothesis. So we know the appropriate VC dimensions for this and this. And these are both from by using the inductive hypothesis. So by induction, we know that pi H1 of n minus 1 is less than or equal to n minus 1 less than or equal to D, and pi H2 of n minus 1 is less than or equal to n minus 1, less than or equal to n minus 1, less than or equal to D minus 1, because that has lower VC dimension, unless we know that pi H of n is equal to, is less than or equal to n minus 1 is less than or equal to D, plus n minus 1 is less than or equal to D minus 1, which is equal to n less than or equal to D, which completes our proof. Okay, I am sorry I ran 2 minutes over, but that does complete this proof. I have a slightly nicerly written set of notes online for this, so you can take a look at that if that was confusing. And tomorrow we'll be coming back and talking about how we can use this to show that so long as your model doesn't have too high of a VC dimension, you have some guarantees on how bad your generalization error can get when you're training on a particular set drawn from a distribution, which is the usual model for classification in machine learning. Class is dismissed, so thank you all very much. I'll see you tomorrow.